So far, all of our statistical tests have examined group differences on an interval ratio scale. With the chi-square test, we're going to calculate a new test statistic, the chi-square, which looks at patterns in categorical variables. Instead of comparing people's scores on some scale, the chi-square test compares which groups people belong to in a categorical variable. Now, specifically, the purpose of the chi-square goodness of fit test is to determine whether the frequency of individuals in these different categorical groups in our population reflects some specific expected values based on our hypotheses. We'll see what I mean by that in a minute. Now, to perform a goodness of fit test, there are, of course, a number of assumptions that must be met. First, for this specific version of the test, you have one categorical variable. Or it could be an ordinal variable, typically if there are only a few levels within that ordinal variable. But this version that we're learning is generally thought of as for categorical variables. Now, there are other chi-square goodness of fit tests, and you can twist this around in some really cool ways. We'll talk about that briefly in a different video, all right? Now, second, the observations are independent. That means whatever category one person is in has nothing to do with the category a different person is in. In a minute, we'll go through an example based on which college different UMaine students are enrolled in. Independent observations means that if Alice is in engineering, it tells you nothing about which college Bob is in. He could be in any of the different colleges. Also, the categories need to be mutually exclusive. This just means that someone can't be in two groups at the same time. You'll see we're literally going to be putting people into little boxes for each group in our categorical variable. And one person can't be in two boxes. Finally, maybe more as a general rule than technically an assumption, but as part of our calculations, we're going to estimate the number of observations or cases or people that you expect to see in each of the different groups. None of the groups should have an expected number of observations that's less than 1, and 80% of the groups should have an expected value of at least 5 observations. And again, while you may not always see it included, I personally like to note that you want a sample that's representative of the population about which you want to infer. If your sample doesn't reflect the population, the numbers may be wrong. So we like random sampling as a way of helping to ensure that that's the case. Plus, it's part of the deeper mathematical assumptions involved in making our inferences back to the population. Now, the hypotheses in a goodness of fit test are very straightforward. Conceptually, the null hypothesis is that the number of individuals in these different categorical groups in the population reflects specific values that the researcher expects to see. And the alternative hypothesis is that at least some of the groups in the population do not reflect those specified values. But we need to be a little more precise than that. To illustrate what I mean, let's introduce a specific research question that we want to use for this example. Let's say that the university wants to better understand students' interest in hockey. The university thinks that the overall interest is the same across all the colleges, and they specifically think that the number of students who attend hockey games is proportional to the number of students in each college. In other words, if we look at students' enrollment by college and see that half of the students are in LAS, Liberal Arts and Sciences, then about half of the students attending hockey games should be from LAS. And if we know that 15% of the students are in education, then 15% of the students attending hockey games should be from education. And if 15% of the students are from engineering and 20% from natural sciences, forestry, and agriculture, NSFA, then about 15 and 20% of the students attending hockey games should be from each of those colleges. If the number of students attending hockey games is proportional to the number of students in each college, and if we then sample students at a game and ask which college they're enrolled in, their answers should be pretty close to these specific values, right? And that's our null hypothesis. Our null hypothesis is that the population of students attending hockey games reflect that specific breakdown. But maybe you don't think attendance is proportional across colleges. You think that students in some colleges may be more interested in hockey than students in other colleges. Some colleges may have more students who work full-time or commute long distances or just study more and can't make the games. Or maybe some colleges just attract fewer hockey fans. Consequently, you don't think that the population of students who attend hockey games reflects those values. And that's our alternative hypothesis. Our alternative hypothesis is that the population of students attending hockey games does not reflect that specific breakdown. So let's write out our hypotheses. Remember, for the chi-square goodness of fit test, we have very specific values that we expect for each category. So our null hypothesis needs to indicate what those specific values are. In this case, our null hypothesis would be something like the proportion of students attending hockey games equals 0.5 for LAS, 0.15 for education, 0.15 for engineering, and 0.20 for NSFA. And our alternative hypothesis would simply be that at least some of those proportions aren't accurate in the population of students who attend hockey games. We're not saying which values are wrong. We're just saying that that population of students who attend hockey games doesn't look exactly like that breakdown. All right? Now, notice a few things. First, we're talking about proportions. So 0.5 equals 50% and 0.15 equals 15%, right? Proportions range from 0 to 1, right? Okay. And notice that if we add up the proportions for each group, they add up to 1 or 100%, just indicating that everyone's in at least one, everyone's in one and only one of those categories. Yes, you could write these down as percentages, but proportions make the math a little cleaner later on, all right? Second, you can see that I've introduced some new notation, pi. In this case, pi is another population parameter, just like mu and sigma squared, but pi is the proportion of the population in a certain group. So notice that our hypotheses are still framed around population parameters, just pi's instead of mu's. And remember, in this case, our population, again, is the population of students who attend hockey games. All right? So we have our hypotheses, and we know the proportions that we expect to see for each category if the null is true. So let's say we go out and sample 200 students at a hockey game and ask them which college they're enrolled in. And we obtain the following results. 105 are in LAS, 35 are in education, 30 are in engineering, and 30 are in NSFA. Now, before breaking, I want to give you a peek at the chi-square formula that we'll be using in our next video. Okay, here it is. Notice the chi-square looks like a kind of a lazy X, but it's the Greek letter chi. The chi-square is equal to the sum of the observed number of cases in a group minus the expected number of cases in that group, right? With that difference then squared and divided by the expected number of cases for that group. And then that result is repeated and summed across all of the different groups, all right? Now, that looks pretty different than what we were doing with the z-tests and the t-test. But if you think about it, conceptually it still is kind of following that theme of how big of a difference did I see? In this case, the difference is the difference between our observed and expected frequency divided by some indicator of what I expected to see. In this case, the expected frequency. All right, now with that, this is a good point to wrap up this video. In our next video, we'll go through the chi-square calculations step by step, determine what our chi-square value is and our p-value, as well as our conclusions. All right, see you then.